Well, good morning, everyone. This is Mr. Fu. Been a long time since I continue with this lecture series. This is the first topic for every JC, but I only took this long to do this because initially I found that this topic is relatively straightforward. So I thought there's no need to do a lecture on it. But I realized that students do have some difficulty doing some of the questions in this topic, though it's a bit more straightforward compared to the subsequent topics. So I'll be doing this, and then if time permits, I will move on to organic chemistry and periodic table. All right. Now, so many concepts here are already covered at O-level. So I'll be very quick in going through those O-level topics. Now, so this is the part that is covered in O-level, where students need to remember the relative mass, relative charge. But what's different between A-level and O-level atomic structure for this section would be there'll be more focus on nuclear fission. So there'll be some questions that test students on balancing the charge after nuclear fission or even nuclear fusion. All right. Now, so I will not go through all these details, which is already covered at O-level. Even for isotopes, I will not go through it. Okay, so if you are interested in the note, you can feel free to message me at fyongwee88@gmail.com. I will not write it down, just remember what I say, fyongwee88@gmail.com. Just for this lecture note, because I'm not going to go through every single detail, even for the examples. Okay, but maybe I'll go through this word example on isotopes. So this is more like an A-level question where you don't really see it in O-level or even some O-level prelim papers. So you have these 4 particles. You are supposed to deduce the particle that have more electrons than protons and more protons than neutrons. So what you can do is deuterium, the information is given here. It have 1 protons, 1 neutrons, and 1 electron. So what you can do here is that you can actually do a simple table. Don't have to draw the line since it's MCQ. Don't need to present in such an orderly manner. So you can write down, then you see which matches. Okay, so for deuterium, negative means it gains 1 electron. The proton remains at 1 because it's just an isotope of hydrogen. All right, and the neutron is 1 because deuterium has 2 nucleons. 2 minus 1 give you 1. Since it gains 1 electron, it becomes 2. So is this correct? More electrons than proton, that's correct. More protons and neutrons, no, so this is out. Because the number of protons and neutrons are the same. Then look at this one, you can do the same thing. Okay, I will not do these two. This is the answer. So proton, you add. The method is the same. So O have 16 nucleons. So you have 8 protons, 8 neutrons plus hydrogen 1, 9. Then there's no neutrons in hydrogen, makes it 8. Electron-wise, 8 plus 1 plus 1, because minus. So you have 10. So this is correct. You have more electrons than protons and also more protons than neutrons. All right. Now, next question, which is an isotope of P? So to be an isotope of P, the number of protons have to be the same, but the number of neutrons will be different. So you work out, since it's an atom with no charge, it's neutral, the number of protons, so I have another column, this is a strategy, will be 11, same number as electrons. All right. And then you just match. So 11, because it gains 2 electrons, so the original number of protons should be only 9, so cannot be Q. As for R, it also cannot be because it actually lost It can be, sorry, it can be, but the number of neutrons happen to be the same, so cannot. So R and P have the same number of protons, but they have the same number of neutrons, so they are not isotopes, they are the same. They are actually, this is actually a charge of this, ion of this one. As 12 electrons, so it gains 1 to become 12, so originally you work backward, it actually gain 1, so it's 11. But because the number of neutrons is 17, so it's S. Okay? Now, this one was covered at O level. We will not go through it. Okay? Just to let you know that for IUPAC, they use carbon 12 as the reference standard for the relative atomic mass. All right? So every atom is divided by this mass to give you the relative mass as you observe. Relative isotopic mass means the relative isotopic mass of the isotope. Nothing much. It's the same as atomic mass, just that we are referring to isotope in particular. And why is the isotopic mass so close to a whole number? That's because the relative masses of the protons and neutrons are both very close to one another, and the electron has a negligible mass. It therefore follows that all relative isotopic masses will be very close to whole number, which are essentially the corresponding nucleon number of the isotopes. So in calculations, the relative isotopic mass of isotope is often approximated by the nucleon number of the isotope. So the two are assumed to be identical, but the most accurate words. Now, what is relative atomic mass? It is equivalent to the weight average mass divided by 1/12 the mass of one atom of carbon 12. All right. So it is also a ratio, so there is no units. This is what you have learned before. And we also learned that the atomic mass is actually an average value of the isotopes in their relative proportions. So I will not go through this. It's like O level. Same thing here. Molecular mass, same thing, very quickly. Not going through formula mass, no. Mole, not really. Mole is supposed to be covered at O level, and you should be very familiar with it at A level already. If not, you'll not be here listening to this lecture. Now, so just to take note of the symbol, then mole is the amount of the substance which contain as many elementary entities. So the entities could be atoms, molecules, ions, or even electrons and other particles. Now, so through experiment, they found out that 12 grams of carbon 12 has 6.02 times 10 to the power 23 carbon atoms. So 1 mole of carbon 12 has 6.02 times 10 to the power 23 carbon 12 atoms. So the definition of mole is 1 mole of substance is the amount of that substance which contains 6.02 times 10 to the power 23 particles. This is known as the Avogadro constant. So Avogadro constant is the constant of proportionality between the number of specific entities and the amount of specific entities of that substance. So the number of specific entities is equal to Avogadro constant multiplied by the amount of specific entities of that substance. So N is the mole. You multiply by Avogadro constant, it gives you the actual number. All right, so I won't go through this. Yeah, it's really very straightforward. Yeah. Molar mass, no. Not going through this anymore. No. For example, no need. Just to be very careful that if the question asks for atoms, it's actually right here times 6 because it's 2 mole. And every 1 mole, you have 3 atoms of water. So you become times 6. The same apply to the rest. Okay. Then for empirical and molecular formula is also covered at O level. So no, you can just read yourself. Percentage composition by mass was covered also, no. But this is the part that I will revisit where you have learned before. Like in the calculation of empirical formula from experimental data, it is common procedure to round off figures to the corresponding nearest whole number in order to get the simplest ratio. The rounding off procedure is usually justified, taking into consideration the possibility of experimental error. Because when we measure mass, sometimes there could be, impurities or mass loss during the experiment. So we need to round off, but there is a limit to how much you round off lah. We cannot just round off everything you want. So there is some strategy lah. So you need to be very careful in how to round off correctly. Okay. So for example, let's say you have the ratio of the amount of the element in the compound to be, let's say this one, 1.51, 3.07, and 1. So some students might just round off to 2, 3, 1, okay, which is not correct. By right, you should times 2 throughout. Yeah. You need to multiply a factor by 2. And not just round off 1.5 to 2. It's too far already. Okay, mathematically wrong. Okay, if you consider the ratio, so you need to times 2 throughout to get this. Okay, if you have 1.33, 3.07, 1, something like that, then you times 3 throughout. All right. You take the smallest, or you can just divide by the smallest number also can. For example, another way is just divide by the smallest one, not smallest one, divide by the middle one, but I think it's easier just to know the factor. Yeah, then this one is times 4. Then this one is times 5. Yeah, just be careful of that. Okay? So at A level, you'll be exposed to a bit more different ratio compared to the O-level questions. O-level questions tend to be more straightforward. Okay, Stoichiometry, no need. This one we will just read on your own. What is limiting reagent? No need. Percentage here, no need. Okay. Avogadro law for gas, no need. Molar volume. Okay, this is new. This part only. So the previously learned concept is volume of the gas at room temperature, 24 dm cube per mole. Okay, that was covered. But there is another condition to take note, that is at standard temperature pressure. So at this condition, the pressure was 10 to the power of 5 Pascal, temperature at 273 Kelvin. So the volume of the gas occupied for 1 mole will be 22.7 dm cube at STP. All right. So the amount of gas can be determined from the volume and the molar volume measured under the same conditions of temperature and pressure. All right. So the amount of gas is equivalent to the volume divided by the molar volume. Okay, and note the conversion of units for volume. Okay, now 6.3 onwards is something I want to emphasize on. This is what will be tested a bit more heavily at A level. The calculations involving combustions of hydrocarbon. So this is the general equation for the complete combustion of hydrocarbon. All right. So the state symbol for hydrocarbon can be either gas or liquid, depending on the hydrocarbon analyzed. Water will be liquid if the measurement was taken at room temperature. If the temperature was greater than 100 degrees Celsius, it will be gaseous state for water. Anyway, so if you have X number of carbon and Y number of hydrogen, right? So all the carbon from the hydrocarbon will be burned to form carbon dioxide, which explains why X. Okay. As for the hydrogen, right? Why is it divided by 2 here? Is because you have a H2 here. So in order to balance the hydrogen between both sides of the equation, you need to divide by 2, okay, to balance the number of hydrogen atoms. So you have Y hydrogen, Y hydrogen. Okay, then look at oxygen. So oxygen was found in both the products, CO2 and water. So O2X. Then for the oxygen here, again, this is O2, this is O2, so just put X here, but you plus here. So the number of moles of oxygen required for the combustion reaction will be equivalent to the sum of the oxygen atoms. So X is O here. So when it comes to O2, need to divide by 4 again. So Y divided by 4. So you have Y over 2 lah. To consider the 2 here. Okay, so the formula is always like that. Just use this formula. It will be easier to carry out the calculations. All right, and the mole ratio equals to the volume ratio. Okay, let's try a question. Look at this question, then we'll try. Okay, so for this question, the important part is the equation. So this methane thiol is a foul-smelling chemical. 20 cm³ of it exploded with 80 cm³ of oxygen. What will be the final volume of the resultant mixture? So this 80 cm³ obviously is in excess, because for 20 cm³ of the methane thiol, right, you only need 60 based on the mole ratio. So you have 20 cm³ of oxygen in excess. And you can do this the ICF method, initial change and F final. So initial volume of this is 20, 80, 00. But you only need to react 60 of it. Since the mole ratio of CO2, SO2 is the same as the reactant gas, so the volume gain is also 20, 20. So the new volume will be 60 cm³. Just add this together. There should be no methane thiol remains. Okay, another example. So you have 10 cm³ of hydrocarbon burned in 100 cm³ of oxygen gas. After reaction, the volume of the gaseous mixture was found to be 80 cm³ when cooled to room temperature. Upon passing the gaseous mixture through aqueous potassium hydroxide, the volume decreased to 50 cm³. So you need to understand what is the purpose of the potassium hydroxide. It is alkaline. So it is used to remove CO2 because CO2 is acidic gas. So the decrease in volume is because CO2 is absorbed by the potassium hydroxide. So the 30 cm³ will be CO2 because you have 80 cm³ after the reaction is completed. And then after passing the gaseous mixture through potassium hydroxide, the volume decreased to 50. So the change in volume is due to the loss of CO2 from the gaseous mixture. That's how you make the deduction. So to do this question, okay, since oxygen was already in excess, so we just put that excess first. Yep, I did this already. So don't need to write this equation. This is just to help you understand what is going on when CO2 is absorbed by the potassium hydroxide. So this is the ionic equation that represents what happened. So the volume of oxygen reacted was 50 cm³. Unreacted 50, sorry. Because the mixture was cooled to room temperature. So the gas mixture don't have water vapor. Okay, because they all condensers. So 80 minus 50 give you the volume of CO2. So the volume of O2 that remains is 50. So 100 minus 50 gives you the volume of oxygen reacted. So if you use this equation, ICS, so initial, so this is the initial volume, 10, 50. Okay, actually they just do this. So 10 is overall, 10 cm³ reacts with 50 cm³ of oxygen. 10 cm³ of hydrocarbon reacts with 50 cm³ of oxygen, form 30 cm³ of CO2. Volume ratio equal mole ratio. So 1:5:3. So what you do is just use algebra to equate 3 is equal to x. And then you substitute x equal to 3 into this equation. 3 plus y over 4 equals to 5. Then you have y over 4 equals to 2. Y equals to 8. Okay. Just use this formula, it will solve a lot of problems quickly. All right. You need to understand that this is the mole ratio. Okay. Okay, I will skip this about concentration. What is it? Yeah, all the relevant equations. But this is something new. Granulated flask. So you are going to start doing practical in chemistry at A level, where you need to prepare standard solution now. And then you will extract out 25.0 cm³ of the solution from the standard solution to do your titration. So that's something new that you will do at A level chemistry practical. So you need to be very familiar with this granulated flask. What does it do? So it's used to prepare standard solution. Okay, so meaning you have a solution of a particular concentration prepared by dissolving the required amount of solute in the solvent. Okay, so now we use the term deionized water. You can also call this volumetric flask. That is also fine. So there are different sizes available in the lab. Okay, the common one is this 250 cm³. So there will be a calibrated marking here for you to see the volume of the solution in the volumetric flask. Okay. Now, let's try this question. Calculate the mass of hydrated magnesium nitrate required to prepare a 250 cm³ of solution containing 0.25 mole per dm³ of nitrate ions. So in order to calculate this, okay, they already mentioned the mole of nitrate ion. Okay, so what you do is you can actually give it a concentration. So you actually can multiply by this volume to give you the mole first, the nitrate ion. Okay, and then how do you work out the number of moles of the hydrated nitrate, magnesium nitrate? Okay, you can see that the mole ratio based on this equation is 1:2. So the number of moles of the hydrated magnesium nitrate will be half of this mole of nitrate ion. Okay, after which you multiply by the molar mass to obtain the mass of the magnesium nitrate hydrated required. As for the next question, you have 6.45 grams of sodium thiosulfate pentahydrate dissolving in deionized water, and the volume make up to 250 cm³ in the volumetric flask. Question: what is the concentration of the sodium thiosulfate solution prepared? And then you work out the concentration of the thiosulfate ions and determine the concentration in gram per dm³. And the last question, if you take out 40 cm³ of the solution and make up to 250 cm³ in another volumetric flask, what will be the concentration of the thiosulfate ions in that new solution? So for this question, first of all, you will work out based on the given mass. Okay, so the molar mass was calculated to be 248.2 grams per mole. And then you calculate the number of moles of this. So you take the mass, divide by the molar mass to obtain the number of moles of the sodium thiosulfate pentahydrate. Okay, and then the amount of sodium thiosulfate pentahydrate is equals to the number of moles of sodium thiosulfate. Mole ratio is the same. And then After which you take the number of moles divided by the volume to get the concentration of the sodium thiosulfate. All right. Okay. To obtain the concentration of thiosulfate in the solution, you need to understand, you could look at the mole ratio, it happens to be the same. The next question, given the molar mass, you just multiply the concentration in mole per dm cube by the molar mass to obtain the gram per dm cube concentration. And then if you want to take out 40 cm cube, right, you need to understand that the concentration that you take out is the same. So you have prepared a standard solution in the volumetric flask, right? Let's say to 250 cm cube. So you use a pipette to take out 40 cm cube. So you need to understand that the solution that you brought out has the same concentration. Okay, the concentration is the same. So you take the concentration, multiply by the volume of the solution extracted, taken out. You get the mole. And then you take this, you divide by the volume. To get a new concentration. Yeah, because after this, right, it is diluted again to another volumetric flask of 250 cm cube. So the number of moles to here is the same. Same mole. Okay? So the number of mole will be the same. What difference is now the concentration? So it will be diluted lah. Okay? Now, you definitely have done titration in your O level. What is different is the word standard solution. The rest of it should be familiar. So the solution that is placed in the burette is referred as the titrant. The one in the conical flask, pipette out, is called the titrant. Yeah, so the spelling is different. Equivalent point is the point where the reaction is completed. Okay, when we use a suitable indicator, the distinct color change occurs at the endpoint. But the endpoint may not be the same as the equivalent point, but we try to have the endpoint very close to equivalent point. So they are almost the same, but not exactly. So in titration, we have 4 types. So just to recap what you learned at O level very quickly. What is the difference between strong and weak acid? The difference here in O level is now we emphasize on the aqueous solution. So as long as it contains water, the strong or weak acid will dissociate. And for basicity of acid, right, other than saying monobasic, dibasic, tribasic, we can also call it monoprotic, diprotic, triprotic. Okay, protic means proton because H plus is a proton. Okay, so that's the difference. Then base, likewise, the same. I don't go through this anymore. Now, but for base, we also have, I don't know whether they got mentioned. Okay, base, right? We also have diacidic, monoacidic, as well as triacidic. Okay, so monoacidic will be your NaOH and NH3, where they dissociate, okay, to form 1 mole of OH minus per 1 mole of alkaline molecule. All right. Then diacidic will be the base with 2 moles. Okay, so These are just for your knowledge lah. It may or may not appear lah. So for example, like barium hydroxide, calcium hydroxide. Okay. The other triacidic ones will be maybe basic, like for example, aluminum hydroxide law. Okay. But aluminum hydroxide is not so soluble lah. Yeah. Now, a recap from O level, the titration curve. So the titration curve shows a graph of pH against volume of the acid or base. It shows how the pH of the acid or base in a conical flask changes when neutralized by the addition of base or acid from the burette. So we have strong acid, strong base, strong acid, weak base, weak acid, strong base, as well as weak acid, weak base titration. Okay, so different titration requires suitable indicators, okay, because their endpoint will differ. Okay, like strong acid, strong base, right? Suitable indicators include phenolphthalein and methyl orange. You can see that the pH jump is quite long. Okay, so you have more suitable indicators. As for strong acid, weak base, the pH jump is smaller in range. Okay, and the final pH, because of strong acid, weak base, the final pH, right, is not reflection of a strong alkaline. It's actually a weak base. If you add excess, equals ammonia. Then phenolphthalein will not be very suitable lah. You have to use methyl orange. In the case of weak acid, strong base, you also do not have a very large pH jump. So the indicators that are suitable will be lesser. You only have phenolphthalein and methyl orange because the pH, because the color change is within a pH not corresponding to the pH jump. So it will not be suitable. So it will change color before the endpoint is reached. So because we are using a strong base, we will see that the final pH is resembling of a strong base. The starting pH with the weak acid will resemble the weak acid because you can see that the pH is not so low, it's about 3. Then for weak acid, weak base, there's no suitable indicator. You must use pH meter connected to a data logger to do the to run the experiment and obtain the titration graph. Yeah. No way. The pH jump is really very small. Although the endpoint is also at 7. But you can see for these two, right? The endpoint is the equivalent point, sorry, is not at 7. Here is at 7. Now, this is something new where you need to use some mathematical calculation. But those who learn additional mathematics, okay, will understand the meaning of logarithm. Basically, it's just to make smaller number more tangible. Okay, because we know that the concentration of H plus or even OH minus is small. So in order to scale it to a more measurable number, we use logarithm. Okay. Now, so I think this was covered in my previous lecture on acid and alkaline. Yeah, I did cover this already. Okay, so you can refer to my lecture on, I think it's called something like acid aqueous solutions chemistry. Yeah, just refer to it. You will have to, there will be more examples to illustrate this. Okay, I will not use this time to go through this. All right, but you have to understand this concept that neutral solution doesn't mean there's no H plus or OH minus, it just means they're equal. Oh, by the way, H plus is just a simplified version. It's actually H3O plus. Yeah, that's what we covered earlier on. Now, the indicators used, right, is in general organic dye stuff, which are actually weak acid and base. And we don't add in large quantity. We only add small quantity. If not, it will really, it will affect the accuracy of the titration results. So the indicator has a pH range over which it changes color. The choice of the indicator depends on the type of titration. Is it strong acid, strong base, weak acid, weak base, weak acid, strong base, etc. And what makes a good indicator? The color change of the indicator must occur when the correct volume of titrant, which is from the burette, is added. You must have the correct volume. The indicator must indicate the correct volume. If not, how it can be an indicator. So the color change takes place only when the reaction completed. And it has to give a very sharp endpoint. The color change has to be distinct. If not, the experimenter cannot see. All right. It will be useless if you need 2 or 3 cm3. You only need 1 drop to make the color, to make the distinct color change, so that you know that's the endpoint. So a suitable indicator is one where its pH range for color change coincides with the region of rapid pH change in the titration curve. In other words, the pH range of indicator must fall on the vertical portion of the titration curve, which I said just now. The choice of indicator where the distinct color change occur, that pH range must be corresponding or within the pH jump of the titration curve. So these are the common indicator, good to know. For theory. For practical wise, phenolphthalein won't be used because it is taken out. But you need to know it for theory as well. So you do not need to memorize the exact pH range, but you need to know the color change, especially for metal orange. If you can remember for screen metal orange, good. Okay? Can? So bromo-thymol blue is another popular indicator. Thymol blue, phenolphthalein, thymolphthalein. And the correct use of indicator is summarized below. Now, I won't go through the calculations. You can just read yourself. Okay, it's the same as what you have done at O level. But this is something new, bed titrations. So bed titration is covered briefly at O level, but it will be more intensively assessed at A level. So since we taught you directly now, bed titrations are usually employed when the determination of the amount of substance poses some difficulty in a direct titration method. For example, let's say you are trying to find out the amount of calcium carbonate in toothpaste. You can't use direct titration because calcium carbonate is insoluble. Or you want to find out the amount of volatile substances like ammonia and iodine. Because during titration, because these are volatile substances, they will be lost and the accuracy will be affected. So what we do in acid-base bed titration is that we will add a quantity of, let's say, base B to a known excess of acid A or vice versa. Okay? Upon mixing, right, the base reacts completely, but because we are using excess acid, so there will be some acid that remains. So the remaining acid will then be titrated with another alkaline, okay, which has its standard concentration known. And from there, you will determine how much acid reacted with alkaline, because you already kind of measure the quantity of A at the start, the volume as well as the concentration. So we can work out the mole and then minus off the mole from the reaction with C to get the mole of acid that reacts with B. So basically, right, the steps is calculate, all right, the mole of C reacted with A. Then calculate the mole of A reacted with C. Okay. After which you subtract mole of A added in step 1 initially to B to subtract from just subtract part 2 the okay, the 3 minus 2, and then work out or calculate the mole of B. Okay. Now, let's look at this word example. You have 3 grams mixture of calcium carbonate and calcium chloride added to 50 cm³ of 1 mole per dm cube of hydrochloric acid. So what reacted was actually the carbonate. Okay. Now, so there was a reaction between carbonate and acid, but there's no reaction between the chloride and the acid. So when 25 cm³ of this solution was titrated with 0.1 mole per dm cube of sodium hydroxide solution, 21.05 cm³ of sodium hydroxide was required for the complete reaction. Calculate the percentage by mass of calcium carbonate. So to do this, you first work out how much sodium hydroxide reacted in the second step, which is the titration step. Excess acid was actually used. It has to be, because what reacted with the sodium hydroxide is the excess acid that is unreacted after its reaction with calcium carbonate. You work out the mole of sodium hydroxide, you work out the acid that reacts with it, and then just take note that, hey, be careful of this, this 25 cm³ of acid that reacted come from 250. So they only take out a portion. So you need to work out the actual mole of acid in the 250 cm³, where it comes from. And then you work out the initial mole of the HCl, and then you minus away, as what I mentioned, subtract away to get the mole of HCl that reacted with the calcium carbonate. And then you work out the number of moles of calcium carbonate that reacted. And then from the mole of calcium carbonate, I think you can quickly find out the mass given the molar mass. And then you just take the mass of the calcium carbonate over the total mass of the mixture to work out the percentage by mass of the calcium carbonate. Now, titration of the carbonate solution. So sodium carbonate is an example of diacidic base because you have, it shows that it actually have 2 steps, okay? It means that it requires 2 moles of H plus to react with it. Yeah. So there are 2 equivalent points in the titration curve. So the reaction of sodium carbonate with HCl can be represented in 2 stages, A and B. Now, in the first stage, the indicator used is phenolphthalein. So Sodium carbonate doesn't react in one step. Since it's a diacetyl base, it reacts in two stages. So the sodium carbonate will first react with HCl to form sodium hydrogen carbonate. So it reacts with 1 mole of H plus first. After the formation of sodium hydrogen carbonate, it reacts with the second mole of H plus. So another H plus in the solution to form the final product. So the overall equation is what you're very familiar with, but it's actually a two-step reaction. Now, which explains you have two endpoints over here in the titration curve. If you use phenolphthalein, it will change color from pink. Phenolphthalein is pink in alkaline, colorless in acid. So if you use phenolphthalein, it will change color from pink to colorless when reaction is completed. So once you see the distinct color change, you stop. Then it will not proceed with stage B. If one stops titration after the distinct color change at this endpoint, all right? If you use methyl orange, it will change color from yellow to orange when both reactions are completed. Because methyl orange is here, it's changing color at the second endpoint here. So when sodium carbonate is completely neutralized to give CO2 and water. So in the first stage, CO2 was not produced yet. So in this stage, the methyl orange does not change color at the end of reaction A. The titration will continue until end of reaction B. That's why when we do titration of acid with sodium carbonate, we use methyl orange. We cannot use phenolphthalein. It will not be able to detect the second endpoint. So from the stoichiometry of the two reactions, it can be seen that if the volume of HCl for the reaction A was X cm cubed, the volume of HCl given the same mole ratio, it will also be the same and the same concentration. Okay, that is an assumption based on the given values. Okay. So the amount of sodium carbonate, you need to understand that whatever sodium carbonate formed in reaction A will go to reaction B, which means that, okay, so if you use phenolphthalein, the volume of HCl will be X cm cubed. If you use methyl orange, will be another X cm cubed. Because everything is 1 mole, 1 mole, 1 mole. So the total volume will be 2x long if you use methyl orange. So this is just to tell you that, okay, if you have a situation where it's all 1:1:1, right? So the different indicator will tells you the different volume of acid required. Yeah. Double indicator method. Okay, so just now we talked about the example of sodium carbonate with HCl. So the double indicator method make use of a two-stage titration to estimate the sodium carbonate in a mixture of sodium carbonate and sodium hydroxide, or a mixture of sodium carbonate and sodium hydrogen carbonate. So let's consider a solution containing both sodium hydroxide and sodium carbonate. So in this case, the concentration of sodium hydroxide and sodium carbonate can be determined by the double indicator method of titration. So the reactions of sodium hydroxide and sodium carbonate with hydrochloric acid are represented by the equations. So in reaction 1, sodium hydroxide reacts with HCl to form NaCl and water. So if you just have something like this, right, it doesn't matter you use phenolphthalein or methyl orange, okay? In reaction 2A, okay, if you have this sodium carbonate with HCl, as we have covered earlier on, you use phenolphthalein, and then you use methyl orange in the second stage. Now, if hydro, so the Y, this is the volume Y, so okay, 2Y lah. If hydrochloric acid is added to a mixture of, so let's say, you see the problem is now is like, you know, the HCl react with both ma. So how do you calculate this? So yeah, you have to use double indicator because you have two reagents mixed together that both can react with HCl. All right, that's the key point here. So if hydrochloric acid was added to a mixture of sodium hydroxide and sodium carbonate, if you use phenolphthalein as an indicator, the pink color decolorizes or discharge when reaction 1 and 2A are completed. In other words, at the first endpoint, the NaOH completely neutralized, sodium carbonate only half neutralized. If you use phenolphthalein, okay? If you use methyl orange later, continue to add, right? You need more, you know. Okay, so after that, right, you get your endpoint, you add methyl orange. Then you will need a further amount of HCl to bring a color change from yellow to the endpoint orange. Okay? It's still alkaline because there's still sodium hydrogen carbonate there. So the amount of acid required for this amount of acid is required for reaction 2B. In other words, at the second endpoint, the sodium carbonate formed by reaction 2A is completely neutralized already. So if you look at the results, right, okay, if you use methyl orange, the amount of HCl to neutralize NaHCO3 in reaction 2B is Y mole. The amount of NaHCO3 which reacted in reaction 2B is equal to how much sodium hydrogen carbonate is formed in 2A, right? So given, okay, you know this is Y, so this is Y, correct? If this is Y, which means that this is Y mole, then this is Y mole. If this is Y mole, this is Y mole. If this is Y mole, this is Y mole. 1:1 ma. Of course, if the situation changes, then you react accordingly lah, like different mole lah. Okay. Yeah. So the amount of sodium carbonate present will be Y mole, Y mole, Y mole. Okay. But that is when you use methyl orange lah. If you use phenolphthalein, okay, phenolphthalein, the total amount of HCl used is only for 1 and 2A. Doesn't occur with 2B. So the amount of HCl reacted with NaOH plus amount of HCl to half neutralize Na2CO3 is X. Okay. So if you want to find out how much NaOH present, you take X minus Y. Okay. So this together is X, which means you use phenolphthalein, both of it. But you know that this alone is Y. Okay. So in order to, so sodium carbonate is Y ma, so this is X. So this one is X minus Y lor. X minus Y will give you how much more of sodium hydroxide reacted. X minus Y give you X minus Y. So X minus Y, X minus Y. Okay. Now let's look at one example to reinforce the understanding. So you have 25 cm³ of solution containing sodium hydroxide and sodium carbonate, titrated against 0.1 mole per dm³ of hydrochloric acid using phenolphthalein as an indicator. After 30 cm³ of acid was used, the indicator was decolorized. Okay, methyl orange was then added. Further 12.5 needed to turn the indicator orange. Calculate the concentration of sodium hydroxide. It's the same as just now. So the amount of HCl to neutralize NaHCO3 will be equal to the amount of HCl to half neutralize Na2CO3 to give NaHCO3. So 12.5 divided by 1000 times the concentration of HCl. This will give you the mole of HCl. The concentration of Na2CO3 will be the number of moles divided by the volume. All right. Because they have the same mole, the Na2CO3 and the HCl. Okay. So the concentration of Na2CO3 is the number of moles of HCl, which is the same, divided by its volume. The volume, this volume, right, is shared by both. So it belongs to both. So you can say this one is 25.0 cm³. This is 25.0 cm³. Same. Okay. All right. So that is the concentration of Na2CO3. The volume of HCl that reacted with NaOH will be 30 minus 12.5. Okay, because the the 12.5 is used to react with the x minus y . From here. In terms of volume. So the total volume minus away that one that react with the, I think the second reaction here. Y would be this one. Then you calculate the amount of HCl that reacted with sodium hydroxide will be 1.75. You take the volume multiplied by the concentration of the acid. Then based on the mole ratio, you can calculate the mole of NaOH present. And then you work out the concentration. That's it. Okay. Now let's move on to the next part on redox reactions. We will just focus on C and D. I think this one is something that we learn also, so I will just skip. Yeah. Okay, we just focus on what is new. Combining two half equation form overall equation was also learned. But what is to take note is that in this reaction, right, the zinc acts as a reducing agent. So it loses 2 electrons, so it was oxidized to zinc 2+. Copper 2+ is the oxidizing agent. It gains 2 electrons and reduced to copper. So you need to understand that the number of electrons or the amount of electrons lost by 1 mole of zinc will be equal to the total amount of electrons gained by 1 mole of copper 2+. So in other words, the total number of electrons lost by the reducing agent will be equal to the total number of electrons gained by the oxidizing agent. Okay. This is something that we have learned before, but the new thing will be electronegativity . So in general, the more electronegative atom will take the negative oxidation number. The less electronegative atom will be the positive oxidation number. Okay, the rest of it was covered in O level. Okay, now just take note, when the question asks for oxidation number, you write the sign followed by the number, but charge is number followed by the charge. So this is, we will just skip through this. Now, let's start with this. Oxidation number of atoms in complicated structure. Okay, this is something new, not tested at O level. Now, we're going to discuss 3 ions here, S2O3 2-, S4O6 2-, and S2OA 2-. Okay, so how do you do this? So you have, okay, we know that oxidation number of oxygen is -2, but how come the sulfur, one is 0, one is +4? Okay, so to do this, right, you need to look at the atoms that's directly bonded to that atom of the element. So for sulfur, you have oxygen here is, oh, there is minus here because 2- means each minus. So this is itself, right, is -2. All right. O- means that this is -1. O-, -1. Here 0. So the sulfur here, this sulfur here, so it's total -2, -1, -1 become -4. So to balance, this will be +4. Then the sulfur on top, right, is here to bonded to here, so 0. So 4 plus 0 divided by 2 give you +2. So for this one, oxidation state, so here minus, so here -2, -2, all right, here -1, so to balance here +5. This one to this one, the electronegativity difference 0, so 0, 0. Here also +5, same situation as here. So 5 plus 0 plus 0 divided by 4, because there's 4 sulfur atoms. For sulfur, of average oxidation number will be 10 divided by 4 plus 2.5. Then we try this one. -2, -2, -1. So here will be +5. Sorry, I forget that's here. So -2 here. Okay. So, but here -2. Okay. Here -1. Why? Because you have an oxygen here. So here, -2, -2. You pull the electron here, pull the electron here. This one, -1, pull electron here. Okay, 1. So it's -2, -2, -1, -1, -6. So here become +6. Likewise here, +6. So +6, +6 divided by 2, +6. Here -1, here also -1. Okay. So the trick to do this is you pick a bond between 2 atoms. The more electronegative atom will gain both the electrons. So it results in a -1 oxidation state. The less electronegative will lose its shared electron, resulting in a +1 oxidation state. Okay. Any question? So if that is the case, then move on. Okay, these are just examples of redox reaction I will not go through, but just to take note that the total increase in oxidation number should be equal to the total decrease in oxidation number. Okay, this is something new. Disproportionation reactions. So in a disproportionation reaction, right, the same element is simultaneously oxidized and reduced, okay, to form two different products. For example, you have chlorine, the oxidation number is 0. It is reduced to -1 and oxidized to +5 simultaneously to form two different products. Okay, likewise for hydrogen peroxide, if you look at oxygen peroxide, in peroxide, oxygen is -1. So it will become 0 oxidized and it will reduce -2. Likewise, the Mn here is +7. So it becomes, this is what? MnO4 minus. So it's going to become plus. Sorry, this is +6. I see wrongly. So this one become +7. 6 minus 8, 2 minus. Here's going to become +4. So this is oxidized. Well, this is reduced. Okay? These are the non-redox reaction where there is no change in oxidation number of any atom. Now, how to balance redox reaction? So all balance equations must satisfy two criteria. Okay? Number one, there must be mass balance. Number two, there must be charge balance. So this is the part that you have to pay attention to. Okay? Balancing redox reactions equation in an acidic medium. So the steps involved is like that. You write the overall unbalanced equation first and assign the oxidation number to all the atoms. Then you construct the unbalanced oxidation and reduction half equations. And then you balance the element reduced or oxidized in each half equation. Balance the oxygen atom by adding water molecules. Balance hydrogen atoms by adding H+ ions. And then you balance the overall charge by adding electron, either as the reactant or product. Then you equalize the total number by multiplying and then add them together. So actually it's easier if I go through the example rather than going through this step. Basically is if you have something like acidic, then the other side you balance with water for the oxygen. If you have hydrogen, then you add H+. So water, H+, you play with it. Okay? So let's say you have this equation. MnO4 minus C2O42 minus in acidic medium. The products, they will tell you Mn2 plus and CO2. So you can see that this and this is related. this and this is related. So the strategy is to write down the half equation first. Okay, then look at it individually. So for this one, you balance log. So you balance the element reduce or oxidize first. Okay. 2, then no need to balance already because I don't even have the O there. Here is okay. But the reduction part here, because you got O here, what did I say there? Balance by adding water. So you have water there to be added. Okay. And then you balance the H atom by adding the H plus ions. All right. So if you have because you see it's an acidic medium, so there will be acid. So it's not enough because you put the water there, correct? Once you put the water there, you need to have the H plus on the left side. Anyway, it's acidic medium. So definitely H plus. Okay. And then what's the next step? You add electrons to balance. Okay. So how many electrons you add? This is 8 plus, 2 plus. So you can consider this minus, so 7 plus minus 2, 5 electrons. And then you need to add the electron here also, because 2 minus to balance the electron. And then you try to equalize the total number of electron gain or loss, because whatever electron loss from the oxidation will go to the reduction. It should be balanced, these two. Okay, then you add them together, you get this. Dun-dun. How about basic medium or alkaline medium? Okay, so in that case, right, the first 6 steps are totally the same. Okay, but the thing is, you need to neutralize the H plus by adding the required number of OH minus to both sides. And then you combine them to form the water, rebalance the half equation by eliminating the common terms, water, and equalize the number of electrons gained and lost. And then add the 2 balanced half equations and eliminate any common terms to obtain the overall balanced equations. Like for example, they may ask you a question like this, alkaline medium, then you form this. So you write down, you know that this one is oxidation. So you need to identify first what is the oxidation and what is the reduction. So disproportionation. Okay. So you divide them first. So for the oxidation half equation, you write I2 plus water. You put water here because you need to balance the O. Remember? Balance the O. I told you just now. Balance the O by adding water. So that's a strategy. Yeah, that's a step. So because got O here, so you write H2O. Then you put H2O, you put a H plus there. You see, the next step, after you put the H2O, must balance the hydrogen by adding H plus on the other side. Something like that. Okay? So you write this, then you write this, then so it's like step 1, then you step 2, then step 3. Okay? Then this is step 4, where you write the electron to balance the charges. You write the electron last. Easier. Don't put it at the beginning. It's very messy. Then because it's 2 minus plus 12. 12 because 6 water. 6 water because this is 6. So this is 2, 3, 6, 6 and 12. So total will be 10. 12 minus 2. Okay. 12 minus 2, 2 plus 2 become plus 12 minus 2 plus 10 minus 10 becomes 0 because the left hand side is 0 charge. Then after that, right, you write the reduction one. I don't have reduction easier than this one. Don't have the water, don't have the H plus, don't have the OH, don't have the H plus, don't have the E minus, don't have the H plus and the water there. So it's less complicated. So you have I2 I minus. So I2 to I minus, you put the 2E minus, reduction, so electron right here. Okay. And then the next step, right, is to neutral, because you see this is alkaline medium. You need to neutralize the H plus by adding the required number of OH minus to both sides, because you don't want the H plus to be there. So it's an alkaline medium, they already said. So what you do here is that you put these two here. These are the two. So that these two become water. H plus or OH might become water, ma. So that you have OH minus on the left hand side, ma, alkaline medium, ma. There you get this one. Okay. And then there is common terms, right? This here got water, here got water, right? So you need to cancel this off. Then this one becomes 6. Okay. And then last step is to actually balance the total number of electrons. So here is 2, here is 2, so here times 5 to get this. And then you just add these two together to get 6. Then 12, the electron gone already. 2, 6 plus 10 I minus En. But you can reduce it to smallest term. Okay, next. So more examples. I think easier than the one on top. No need to write state symbol. You can write like that, impressive already. Okay, after that, right, you just write down, they ask you to write the balance, oxidation, reduction, half equations. So you must first look at the equation and see which is oxidized and reduced. This is oxidized, this is the first step. And obviously this is reduced. And obviously there will be this part got the water H plus down there. Okay, put the water here, then put the H plus here. Correct? Yeah. Then you just balance. Next thing, basic. So must know what is the oxidation. Obviously, this is the oxidation because Zn becomes Z2 plus. This one is the reduction. Okay, and then obviously because of OH here, you need to put OH here. Yeah. Then the NO3, because you have H here, you put the water here, then you put the water there. Because it's basic medium, you put the OH minus on there. And then you just balance this. Okay. Okay, so NO3 here. So basically you write this one first. You skip the step lah. Okay, that's the first step. And then you notice that the NO3 minus here got H here. So remember what we thought just now? The H, what happened? Okay, the H balanced by the H plus. Oxygen balanced by the H2O. So you have H here, you can put a H2O here first. You have H2O here, then you must know that O, then you must have a OH minus. Okay, and then you start to balance. So this is 3. There, O4, how to balance this? Okay, then you can put you put a 6 here. Okay, so this one is okay, and nitrogen okay. Oxygen 3, 4, 4. You maybe put a 4 here, but the charge is not balanced. 4 here, the H is still not balanced. Yeah, so what you do here, you can increase to something, make this a very nice number, up log 6, then 3, 9, and then to balance the electron, you put a 8 minus here. Okay, you just balance these two to get this. Now, determination of oxidation number using half equation. So in a redox reaction, which involves transfer of electrons, the number of electron transfer is related to the change in oxidation number of the atom, oxidize or reduce, like this. Okay. So the oxidation number of zinc in the reactant is equal to the oxidation number of zinc in zinc 2+. It's related. Oxidation number of copper in copper 2+ plus minus 2 give you oxidation number of the copper in product. So the you can add like that, you know what I mean? Yeah, it's sum of the oxidation number. So one example, right? You have this unbalanced reduction half equation. What is the oxidation number of the product? So you know this is this thing, right, is +7 +5. So 7 minus 5 give you +2. That's what you get. As for this one, oxidation number of PB in reactant Y, it will be PB itself here is +4. So +4 minus 2 give you +2. Okay, let's look at this example, a long question. You have the reduction of chlorate ion in aqueous solution. So it was found that 25 cm³ of 0.05 mole per dm³ of potassium chlorate require 50 cm³ of 0.2 mole per dm³ of aqueous titanium chloride. And then the titanium ion is oxidized to titanium 4 ion in the reaction. Which formula represent the reduction product? Okay, you need to calculate the mole. So you calculate the mole of ClO4 minus first. You will get 25 divided by 1000 times the concentration. And then you calculate the mole of titanium 3+, which is also given. Then you compare the mole ratio is 1:8. Then you construct a balanced half equation to find out the total number of electron transfer. So titanium 3+ become titanium 4+. That's what is mentioned. So there is actually a loss of 1 electron. So oxidation half equation, right? Because you see titanium 3+ here is 8. So I put it as 8 to balance. So the amount of electron lost by 8 mole of titanium, because there's 8 mole of titanium 3+, man. So you need to understand that you need to convert that to 8. So 8 mole of electron loss, which means that your ClO4 minus, for 1 mole of ClO4 minus, right, it gains 8 mole of electron. So with that, right, you work backward law. So the oxidation number is X. I don't know what is it. So X minus 8 become the product. Hey, the X is given, sorry. It should be, sorry, it's given already. Sorry, it's +7. So 7 minus 8 give you -1. So the corresponding one would be this one. Okay. A more complicated example. So you have 1 mole of S2O3 2-, and this reduces 4 mole. So we give you the mole ratio directly. No need to calculate mole directly. So but this one, right, you have to be very careful. Just now, right, is everything, you know, this one and the Cl is only 1. But this one, right, is 2 sulfur. Okay, be careful there. So it's a bit different. So amount of S2O3 2- is 1 mole. Amount of Cl2 is 4 mole. Mole ratio 1:4. So you construct the half equations. Cl2 become 2 Cl-. And because there are 4 moles of Cl2, the number of moles of electron transfer is 8. which means that your S2032 minus is losing 8 electrons. Yeah. So S here is +4. The oxidation state. +4 times 2 plus 8 minus 6 give you -2. Okay, correct. So +4. So you have the product will be like this is X. So +4 equals to X minus 8 because electron minus 8 ma. So X equals to 4 plus 8 plus 12. But because they are 2s, so it should be actually 2x here. So 2x equals to +12, x equals to +6. Because 2x as they are 2s. Get it? Yeah, they are 2 sulfur atoms. Okay? There are 2 sulfur atoms. Okay, now next one. Now you have to calculate the mole using the quantity they give. So in the experiment, H2S reacted with how many more to go? Okay, 24 cm³ of 0.10 mole per dm³ of bromine containing ion BrOX minus in an acidic medium. The product form is Br2 and 0.289 gram of sulfur. What is the value of X in BrOX minus? So calculate lah. So H2S and S have the same mole. So if you find out H2S, you will find out the mole of S as well. So you take 0.289 divided by 32.1. Yes. Which gives you the number of moles of S. Because they said that sulfur is 0.289. So, but the mole is the same lah, because 1:1 ma. Okay. Now, then the amount of BrOX minus, you can calculate again to get this one. So the molar ratio is of H2S to BrOX is 5:2, 2.5 to 1. Okay, so oxidation, half equation, H2S become S plus, because it's acidic medium, right? So to balance the H, you put a H plus here. There's no O, don't care about water. And then 2E minus, okay, with oxidation ma. Because they said that, okay, H2S to become S, right, is confirmed oxidation ma, because S is -2, this one is 0. So this one is oxidation. And then because there are 5 mole of H2S involved, so I times 5 throughout. So later easier to add the 2 half equations together. So for the other one, BrOX minus to Br2, remember there is, I don't think this balanced, but doesn't matter, right? Yeah, because definitely, yeah, water then H plus, then no need to do the half equation, combine the half equation. I'm not asking you to combine that. If combine, then you need to add water and then after that add H plus here. Yeah, very troublesome. After that is this one become Br2. So yes, you can just write in terms of this easier. Okay, now so 10 electrons. Okay, the number of electrons transferred should be the same. Let the oxidation number of Br be BrOS be N. So N plus -5 give you 0. Okay. N plus -5 give you 0. So N equals to +5. Okay. How do you get this is based on this one. Okay, so I think I'll choose this easier. Because 5 electron ma, minus 5. So this is the N, this is 0 ma. So you get this from here, easier to see. So N minus 5 gives you 0. So N is plus 5. Okay? Or you can do that also lah. 2N minus 10 equals 0. You still get N equals to plus 5 lah. It's the same. So now you know that this is plus 5. So balancing the oxidation number. So plus 5 plus X times minus 2 give you minus 1. Consider this ion. Okay, and you get X equals to 3. Okay. All right. Redox titration. We've done this at O level before. So I will just quickly go through part of it. Okay, this is done already. So basically, the new thing is the number 2 one, not very familiar. But we did the equation just now, if I'm not wrong. Okay, so this is what happened in acidic medium. The magnetic ions reduced to Mn2+. Normally in titration, we see a faint pink, not exactly colorless. But theory-wise, you put that colorless, right? Yeah. You can't use HCl because the problem is the Cl minus can also be oxidized by KMnO4 to Cl2. So if that is going to be used, it will result in less mole of KMnO4 remains because it reacted, ma. Yeah. Yeah, and then the titration result will be affected. If the KMnO4 is in the burette, right, the titrant, right, then volume of KMnO4, okay, to react because of less mole will be more than expected. Yeah. Because you actually have lower concentration. If this is the titrant. If HNO3 is not used because result in, because HN3 is an oxidizing agent, reacts with a reducing agent in the conical flask, titrant. So it will result in also less because you need less, it will be like lower volume of KMnO4 recorded than expected. Provided this is the titrant. Okay. But in neutral alkaline medium, you will see MnO4 minus reduced to solid MnO2, brown or black solid. Okay. Next. So if you have the burette with the KMnO4, if you have Fe2+, right? But Fe2+ itself is okay, oxidized, right? Fe2+, a bit, it appear yellow. Then you will turn pink. Oh, okay. The mixture of it will be actually a bit yellow. And then if it's H2O2, it will be colorless to faint pink. If it's the conical flask is the KMnO4, right? Orange to yellow because Fe3+ is yellow. Yeah, it will be orange at first, pink because of the KMnO4. Then for here will be pink to colorless. Okay. Now just work out this example. Then we are done. Okay, still got how many more to go? Oh, just go through all the examples lah. Then we are done. Okay. Finishing soon. Okay, I think this one you all just read yourself. Yeah, because it's quite straightforward lah. Yeah. Then you go through dichromic titrations. All right. So potassium, this is only in theory, not in practical. It will not be tested in practical. So the orange solution turned green. Unlike KMnO4, right, the problem with K2Cr2O7 is not self-indicating. So you need an indicator because the problem is, right, it's very hard to judge the endpoint. The green will predominate long before reduction completed. So it's not going to be accurate. So we actually use the indicator, but no need to know this. Okay, so let's say you have this question. You have iron 2 plus in the conical flask, the titran. Then you have this concentration of dichromate. First of all, you calculate the amount of Cr2O7 2 minus reacted. Then given this one, this will be provided normally. Yeah, unless they have a separate question ask you to write. You don't have to memorize this. Okay, and then Fe2 plus is 6 times mole of this. And then iron and iron 2 plus should have the same mole. Then you multiply by the molar mass to get the mass, and then you divide by the mass of the iron to get the percentage purity. Next possible titration that will come out is iodine thiosulfate, which is done at O level again. Okay, for this one, right, if you recall what you have done at O level, at near the endpoint, they will ask you to add starch, if you remember. And then because brown to color is not so apparent, so they add starch to form the blue starch iodine complex, so that the color change from blue, black to colorless be very obvious. Yeah, it's called the iodometric titration. So for this one, right, the color change, if you do want to use indicator starch, then it will just be pure yellow to color, which is very difficult to see. You must definitely add starch, but don't add too much, okay? So when you add starch, the iodine and starch form a blue-black solution. You call that the complex. And then the titration is then continue until 1 drop of thiosulfate changes the color of reaction mixture from blue-black to colorless. Okay? This one I won't. You cannot add the starch at the beginning because what happens is that the iodine will be trapped in the starch molecule. Yeah, and it will not react. Yeah. When set aside, it will become blue again. Just ignore because the iodide, excess iodide will oxidize. So this is just an example. I think I won't go through this. It's just more concept. Then the last one is precipitation titration. So the two solutions will react to form the precipitate of an insoluble salt. That is possible. For example, silver chloride. So this is a Morse method. So this is just possible. Actually, you can use titration for precipitation. Okay, that's it for today. I won't go through the specific one example. I just give you the answer. You can just try yourself. Like this one, the final answer, then work out yourself to practice. All right. That's it.